Hey guys, I'm back. Let me continue with the book Deep Reading on chapter 8.2 Low Level I/O Middle School Read and Write. The lowest level of I/O in Unix provides no buffering or any other service. It is in fact a direct entry into the operating system. All input and output is done by two functions called read and write. For both, the first argument is a file descriptor. The second argument is a buffer in your program where the data is to come from or go to. Third argument is the number of bytes to be transferred. The codes are like this. Each code returns the byte count, which is the number of bytes actually transferred. On reading, a number of bytes returned may be less than the number asked for. A return value of 0 bytes implies in the file and -1 indicates an error of some sort. For writing, the returned value is the number of bytes actually written. It is generally an error if this isn't equal to the number supposed to be written. The number of bytes to be read or written is quite arbitrary. The two most common values are 1, which means one character at a time, unbuffered, and 512, which corresponds to a physical block size on many peripheral devices. This later size will be most efficient, but even character at a time as natural is not inordinately expensive. Hang on. Putting these facts together, we can write a simple program to copy its input to its output. The equivalent of the file copying program written for Chapter 1 in Unix. This program will copy anything to anything. Since the input and output can be redirected to any file or device, if the file size is not a multiple of bus size, some read will return is a smaller number of bytes to be written by write. The next call to read after that will return 0. It is instructive to see how read and write can be used to construct higher level routines like getChar, putChar, etc. For example, here is a version of getChar which does unbuffered input. C must be declared char because read accepts a character pointer. The character being returned must be masked with 0377 to ensure that it is positive. Otherwise, sign extension may make it negative. The constant 0377 is appropriate for the PDP-11, but not necessarily for other machines. The second version of get char does input in big chunks and hands out the characters one at a time. 4.3 Open, create, close, and ink. Other than the default standard input, output, and error files, you must explicitly open files in order to read or write them. There are two system entry points for this, open and create. Open is rather like the fopen discussed in Chapter 7, except that instead of returning a file pointer, it returns a file descriptor, which is just an int. As with fopen, the name argument is a character string corresponding to the external file name. The access mode argument is different. However, read mode is 0 for read, 1 for write, and 2 for read and write. Open returns -1 if any error occurs. Otherwise, it returns a valid file descriptor. It is an error to try to open a file that does not exist. The entry point create is provided to create new files or to rewrite old ones. Returns a file descriptor if it was able to create the file called name and -1 if not. If the file already exists, create will truncate it to zeroness. It is not an error to create a file that already exists. If the file is brand new, if the file is brand new, creates it with the protection mode specified by the per mode argument. In the Unix file system, there are 9 bits of protection information associated with a file, controlling read, write, and execute permission for the owner of the file, for the owner's group, and for all others. Thus, a 3-digit octal number is most convenient for specifying the permissions. For example, 0755 specifies read, write, and execute permission for the owner, and read and execute permission for the group and everyone else. To illustrate, here is a simplified version of the Unix Autodidactism, a program which copies one file to another. The main simplification is that our version copies only one file and does not permit the second argument to be a directory. Like these words. This is a named, typically 15 to 25, on the number of files which a program may have opened simultaneously. Accordingly, any program which tends to process many files must be prepared to reuse file descriptors. The routine close breaks the connection between a file descriptor and an open file, and frees the file descriptor for use with some other file. Termination of a program by exit or return from the main program closes all open files. The function init file name removes the file name from the file system. Exercise 8-minute score 1. Rewrite the program kit from Chapter 7 using read, write, open, and close instead of their standard library equivalents. Perform experiments to determine the relative speeds of the two versions. 8.4 Random access seek and else seek. File inertial is normally sequential. Each read or write takes place at a position in the file right after the previous one. When necessary, however, a file can be read or written in any arbitrary order. The system called lseek provides a way to move around in a file without actually reading or writing. Forces the current position in the file whose descriptor is FD to move to position offset, which is taken relative to the location specified by origin. Subsequent reading or writing will begin at that position. Offset is along, FD and origin are ends. Origin can be 0, 1, or 2 to specify that offset is to be measured from the beginning, from the current position, or from the end of the file respectively. For example, to append to a file, seek to the end before writing. To get back to the beginning, notice the 0L argument. It could also be written as non-zero. With lseek, it is possible to treat files more or less like large arrays at the price of slower access. For example, the following simple function reads any number of bytes from any arbitrary place in a file. In pre-version 7 Unix, the basic entry point to the inertial system is called seek. Seek is identical to lseek, except that its offset argument is an int rather than a long. Accordingly, since PDP-11 integers have only 16 bits, the offset specified for seek is limited to 65535. For this reason, origin values of 345 cause seek to multiply the given offset by 512, the number of bytes in one physical block, and then interpret origin as if it were 0, 1, or 2 respectively. Thus, to get to an arbitrary place in a large file requires two seeks. First one, which selects the block, then one which has origin equal to 1 and moves to the desired byte within the block. Exercise 8-minute score 2. Clearly, seek can be written in terms of lseek and vice versa. Write each in terms of the other. 8.5 Example and implementation of fopen and getC. Let us illustrate how some of these pieces fit together by showing an implementation of the standard library routines fopen and getC. Recall the files in the standard library are described by file pointers rather than file descriptors. A file pointer is a pointer to a structure that contains several pieces of information about the file. A pointer to a buffer, so the file can be read in large chunks. A count of the number of characters left in the buffer. A pointer to the next character position in the buffer. Some flags describing read/write mode, etc., and the file descriptor. The data structure that describes a file is contained in the file style.h, which must be included by #include in any source file that uses routines from the standard library. It is also included by functions in that library. The following excerpt in the following excerpt from style.h names, which are intended for use only by functions of the library, begin with an underscore, so they are less likely to collide with names in the user's program. Okay, so long. So many words. The getC macro normally just decrements the count, advances the pointer, and returns the character. A long hash define is continued with a backslash. If the count goes negative, however, getC calls the function fillBuff to replenish the buffer, reinitialize the structure contents, and return a character. A function may present a portable interface, yet use self-contained non-portable constructs. getC masks the character with 0377, which defeats the sign extension done by the PDP-11 and ensures that all characters will be positive. Although we will not discuss any details, we have included the definition of putC to show that it operates in much the same way as getC, calling a function flashBuff when its buffer is full. The function fopen can now be written. Most of fopen is concerned with getting the file opened and positioned at the right place, and setting the flag bits to indicate the proper state. fopen does not allocate any buffer space. This is done by fillBuff when the file is first read. So many words. The function fillBuff is rather more complicated. The main complexity lies in the fact that fillBuff attempts to permit access to the file even though there may not be enough memory to buffer the initial. If space for a new buffer can be obtained from clloc, all is well. If not, fillBuff does unbuffer its initial using a single character stored in a private array. Okay. The first call to getC for a particular file finds a count of 0, which forces a call of fillBuff. If fillBuff finds that the file is not open for reading, it returns EOF immediately. Otherwise, it tries to allocate a large buffer, and finding that a single character buffer, setting the buffering information in flag appropriately. Once the buffer is established, fillBuff simply calls read to fill it, sets the count and pointers, and returns the character at the beginning of the buffer. Subsequent calls to fillBuff will find a buffer allocated. The only remaining loose end is how everything gets started. The array IOB must be defined and initialized for sting, start, and stir. And The initialization of the flag part of the structure shows that string is to be read, style is to be written, and stir is to be written and buffered. Exercise 8 middle score 3. Rewrite f open and fill buff with fields instead of explicit bit operations. Exercise 8 middle score 4. Design and write the routines flash buff and fclose. Exercise 8 middle score 5. The standard library provides a function which is identical to lseek except that fp is a file pointer instead of a file descriptor. Write fseek, make sure that your fseek coordinate is properly with the buffering down for the other functions of the library. 8.6 example, listing directories. A different kind of file system interaction is sometimes called for determining information about a file, not what it contains. The Unix command ls list directory is an example. It prints the names of files in a directory and optionally other information such as sizes, permissions, and so on. Since on Unix a listed directory is just a file, there is nothing special about a command like ls. It reads a file and picks out the relevant parts of the information it finds there. Nonetheless, the format of that information is determined by the system, not by a user program. So ls needs to know how the system represents things. We will illustrate some of this by writing a program called fsize. Fsize is a special form of ls which prints the sizes of all files named in its argument list. If one of the files is a directory, fsize applies itself recursively to that directory. If there are no arguments at all, it processes the current directory. To begin a short review of file system structure, a directory is a file that contains a list of files names and some indication of where they are located. The location is actually an index into another table called the node table. The node for a file is where all information about a file except its name is kept. A directory entry consists of only two items, a node number and the file name. The precise specification comes by including the file sys/dir.h, which contains type ino_t is a type div describing the index into the inode table. It happens to be assigned on PDP 11 Unix, but this is not the sort of information to embed in a program. It might be different on a different system. Hence, the type div, a complete set of system types, is found in sys/types.h. The functions stat takes a file name and returns all of the information in the node for that file, or -1 if there is an error. That is, fills the structures to stbuf within not information for the file name. The structure describing the value returned by stat is in sys/stat.h, and it looks like this. Most of these are explained by the comment fields. The st_mode entry contains a set of flags describing the file. For convenience, the flag definitions are also part of the file sys/stat.h. Now we are able to write the program fsize. If the mode obtained from stat indicates that a file is not a directory, then the size is at hand and can be printed directly. If it is a directory, however, then we have to process that directory on file at a time. It in turn may contain subdirectories, so the process is recursive. The main routine, as usual, deals primarily with command line arguments. It hands each argument to the function fsize in the bigger buffer. The function fsize prints the size of the file if the file is a directory. However, fsize first calls directory to handle all the files in it. Note the use of the flag names s_ifmt and s_ifdir from stat.h. Okay, the function directory is the most complicated. Much of it is concerned, however, with creating the full path name of the file being dealt with. Like this first, if a directory slot is not currently in use because the file has been removed, the not entry is 0, and this position is kept. Each directory also contains entries for itself call and its parent. Clearly, this must also be skipped, or the program will run for quite a while. Although the fsize program is rather specialized, it does indicate a couple of important ideas. First, many programs are not system programs. They merely use information whose form or content is maintained by the operating system. Second, for such programs, it is crucial that the representation of the information appear only in standard header files like stat.h and dir.h, and that programs include those files instead of embedding the actual declarations in themselves. Is 8.7 Example: a storage allocator. In chapter 5, we presented a simple-minded version of a log. The version which we will now write is an restricted calls to a log and free, may be intermixed in any order. A log calls upon the operating system to obtain more memory as necessary. Besides being useful in their own right, these routines illustrate some of the considerations involved in writing machine-dependent code in a relatively machine-independent way, and also show a real-life application of structures, booleans, and typediff, rather than allocating from a compiled in fixed-sized array a log will request space from the operating system as needed, since other activities in the program may also request space. Asynchronously, the space a log manages may not be contiguous. Thus, its free storage is kept as a chain of free blocks. Each block contains a size, a pointer to the next block, and the space itself. The blocks are kept in order of increasing storage address, and the last block, highest address, points to the first. So the chain is actually a ring. A ring, not a chain, a ring. When a request is made, the free list is scanned until a big enough block is found. If the block is exactly the size requested, it is unlinked from the list and returned to the user. If the block is too big, it is split and the proper amount is returned to the user, while the residue is put back on the free list. Hang on. If no big enough block is found, another block is obtained from the operating system and linked into the free list. Searching them resumes. Freeing also causes a search of the free list to find the proper place to insert the block being freed. If the block being freed is adjacent to a free list block on either side, it is classed with it into a single bigger block, so storage does not become too fragmented. Determining adjacency is easy because the free list is maintained in storage order. One problem which we alluded in chapter 5, is to ensure that the storage returned by a log is aligned properly for the objects that will be stored in it. Although machines vary, for each machine there is a most restrictive type. If the most restricted type can be stored at a particular address, all other types may be also. For example, on the IBM 360/370, the Honeywell 6000, and many other machines, any object may be stored on a boundary appropriate for a double. The PDP-11 int suffix on the PDP-11 int suffixes. A free block contains a pointer to the next block and a chain, a record of the size of the block, and then the free space itself. And the control information at the beginning is called the header. To simplify alignment, all blocks are multiplies of the header size, and the header is aligned properly. This is achieved by a union that contains the desired header structure and an instance of the most restrictive alignment type. In a log, the requested size in characters is rounded up to the proper number of header-sized units. The actual block that will be allocated contains one more unit for the header itself, and this is a value recorded in the size field of the header. Pointer returned by a log points at free space, not at the header itself. The variable base is used to get started if a log p is null, as it is at the first call of a log. Then a degenerate free list is created. It contains one block of size 0 and points to itself. In any case, the free list is then searched. The search for a free block of adequate size begins at the point a log p, where the last block was found. This strategy helps keep the list homogeneous. If a too big block is found, the tail end is returned to the user. In this way, the header of the original needs only to have its size adjusted. In all cases, the pointer returned to the user is to the actual free air, which is 1 unit beyond the header. Notice that p is converted to a character pointer before being returned by a log. Function more core obtains storage from the operating system. The details of how this is done, of course, vary from system to system. In Unix, the system entry SBRK returns a pointer to n more bytes of storage. The pointer satisfies all alignment restrictions. Since asking the system for memory is a comparatively expensive operation, we don't want to do that on every call to a log, so more core rounds up the number of units requested of it to a large value. This large block will be chopped up as needed. The amount of scaling is a parameter that can be tuned as needed. SBRK returns -1 if there was no space. Even the null would have been a better choice. The -1 must be converted to an int so it can be safely compared. Again, cases are heavily used, so the function is relatively immune to the details of pointers representation on different machines. Free itself is the last thing. It simply scans the free list, starting at a log p, looking for the place to insert the free block. This is either between two existing blocks or at one end of the list. In any case, if the block being freed is adjacent to either neighbor, The adjacent blocks are combined. The only troubles are keeping the pointers pointing to the right things and sizes correct. So many words. Although storage allocation is intrinsically machine dependent, the code shown above illustrates how the machine dependencies can be controlled and confined to a very small part of the program. And the use of type diff in union handles alignment, given that SBRK supplies an appropriate pointer. Case arrange that pointer conversions. Case arrange that pointer conversions are made explicit and even cope with a badly designed system interface, even though the details here are related to storage allocation. The general approach is applicable to other situations as well. Exercise 8 score 6. The standard library function clock returns on pointer to n objects of size with the storage initialized to 0. Write clock using a log either as a model or as a function to be called. Exercise 8 score 7. A log accepts a size request without checking its plausibility. Free believes that the block it is asked to free contains a valid size field. Improve these routines to take more pains with error checking. Exercise 8 score 8. Write a routine be free, which will free an arbitrary block P of n characters into the free list maintained by alloc and free. By using bfree, a user can add a static or external array to the free list at any time. Okay, finally, appendix. See reference manual. Do I have to read this? I think I shall. I think I should. I think I have to. 1. Introduction. This manual describes the C language and the DZPDP-11, the Honeywell 6000, the IBM system /370, and the Interdata 8/32. Where differences exist, it concentrates on the PDB-11, but tries to point out implementation-dependent details, with few exceptions. These dependencies follow directly from the underlying properties of the hardware. The various compilers are generally quite compatible. 2. Lexical conventions. There are 6 classes of tokens: identifiers, keywords, constants, strings, operators, and other separators, blanks, tabs, new lines, and comments, collectively white space. As described below are ignored except as they serve to separate tokens. Some white space is required to separate otherwise adjacent identifiers, keywords, and constants. If the input stream has been placed into tokens up to a given character, the next token is taken to include the longest string of characters which could possibly constitute a token. 2.1 Comments. The characters /* introduce a comment which terminates with the characters */ comments do not nest. 2.2 Identifiers. Names. An identifier is a sequence of letters and digits. The first character must be a letter. The underscore counts as a letter. Upper and lowercase letters are different. No more than the first 8 characters are significant, although more may be used. External identifiers, which are used by various assemblers and loaders, are more restricted. 2.3 Keywords. The following identifiers are reserved for use as keywords and may not be used otherwise. The entry keyword is not currently implemented by any compiler, but is reserved for future use. Some implementations also reserve the words Fortran and ASM. 2.4 Constants. There are several kinds of constants are listed below. However, characteristics which affect sizes are summarized in Chapter 2.6. 2.4.1 Integer constants. An integer constant consisting of a sequence of digits is taken to be octal if it begins with 0. Decimal. Otherwise, the digit 8 and 9 have octal value 10 and 11 respectively. A sequence of digits preceded by lower 0x or upper 0x by 0 lower x or 0 upper x. A sequence of digits preceded by 0 lowercase x or 0 uppercase x, digit 0, is taken to be a hexadecimal integer. The hexadecimal digits include lowercase a or uppercase a through lowercase f or uppercase f with values 10 through 15. A decimal constant whose value exceeds the largest sign machine integer is taken to be long. An octal or hex constant which exceeds the largest unsigned machine integer is likewise taken to be long. 2.4.2 Explicit long constants. A decimal, octal, or hexadecimal integer constant immediately followed by L, by lowercase l or uppercase L, is a long constant. As discussed below, on some machines, integer and long values may be considered identical. 2.4.3 Character constants. A character constant is a character enclosed in single quotes, as in single quote is lowercase x. The value of a character constant is the numerical value of the character in the machine's character set. Certain non-graphic characters, the single quote, and the backslash may be represented according to the following table of escape sequences. The escape backslash DDD consists of the backslash followed by 1, 2, or 3 octal digits, which are taken to specify the value of the desired character. A special case of this construction is backslash 0, not followed by a digit, which indicates the character NUL. If the character following a backslash is not one of those specified, the backslash is ignored. 2.4.4 Floating constants. A floating constant consists of an integer part, a decimal point, a fractional part, and lowercase e or uppercase e, and an optionally assigned integer exponent. The integer and fraction parts both consist of a sequence of digits. Either the integer part or the fraction part, not both, may be missing. Either the decimal point or the lowercase e and the exponent, not both, may be missing. Every floating constant is taken to be double precision. 2.5 Strings. A string is a sequence of characters surrounded by double quotes, as in double quotes ... A string has type arrays of characters and storage class static. See chapter 4 below, and is initialized with the given characters or strings even when written identically or distinct. The compiler places a null by \0 at the end of each string so that programs can scan the string, can find its end. In a string, the double quote character must be preceded by a lowercase a backslash. In addition, the same escapes as described for character constants may be used. Finally, lowercase a backslash and an immediately following new line are ignored. 2.6 Hardware characteristics. The following table summarizes certain hardware properties which vary from machine to machine. Although these affect program portability, in practice they are less of a problem than might be thought a priori. Like this, for these four machines, floating point numbers have 8-bit exponents. 3. Syntax notation. The syntax notation used in this manual, syntactic categories are indicated by italic type and literal words and characters in board type. Alternative categories. Alternative categories are listed on separate lines. An optional terminal or non-terminal symbol is indicated by the subscript OPT, so that like this indicates an optional expression enclosed in braces. The syntax is summarized in chapter 18. For what is in the name? C bases the interpretation of an identifier upon two attributes of the identifier, its storage class and its type. The storage class determines the location and lifetime of the storage associated with an identifier. The type determines the meaning of the values found in the identifier storage. There are 4 declarable storage classes: automatic, static, external, and register. Automatic variables are local to each invocation of a block and are discarded upon exit from the block. Static variables are local to a block but retain their values upon re-entry to a block even after control has left the block. External variables exist and retain their values throughout the execution of the entire program and may be used for communication between functions, even separately compiled functions. Register variables are, if possible, stored in the fast registers of the machine. Like automatic variables, they are local to each block and disappear on exit from the block. C supports several fundamental types of objects. Objects declared as characters are large enough to store any number of the implementation's character set, and if a genuine character from that character set is stored in the character variable, its value is equivalent to the integer code for that character. Other quantities may be stored into character variables, but the implementation is machine dependent. Up to 3 sizes of integer declared: short int, and long int are available. Longer integers provide no less storage than shorter ones, but the implementation may make either short integers or long integers, or both, equivalent to plain integers. Plain integers have the natural size suggested by the host machine architecture. The other sizes are provided to meet special needs. Okay, here I'm gonna have a break. Okay, see you guys. Goodbye.